Okay, we can start this session. Um, First of all, I would like to thank you all for being here, and I will I would ask all the speakers to please follow keep the timeline, because after this session we have the main panel session that is beginning immediately, so we don't have any time for any time to compensate. So our first speaker today is Benjamin Koch, and he will be telling us about vacuum energy, Casimir effect, and Newton's non-constant. So please.
Much. Of course, I want to thank you in the first place to come here after lunch break and Friday and so on, and also the organizers for the opportunity to talk at this conference. And the title has been mentioned. It is about a work which has been done in collaboration with René Sedmik and Mario Pitschmann and Christian Käding. And let's just jump into it. So the short outline for this talk. First, to start off, I want to tell, okay, what we know, what we think we know, and what we would like to know. Then I want to clearly formulate the hypothesis, how I want to address these questions. And then at third point, I will present a framework, which is a framework particularly suited to include the two hypotheses I mentioned. And when the framework is set, I will study the Casimir effect, and then even look towards experiment. And then hopefully some questions, discussion, and conclusions. So vacuum energy. What do we know so far? So first of all, we think we know that there's a quantum vacuum, and the experimental evidence most famously was given here by Casimir. And what you measure in the end is that you have this quantum energy and it can accelerate plates. So if we look at the other, okay, I moved to the wrong spot. So cosmological vacuum. Well, it's about, we have heard a lot about it here in the context of this conference. It's about cosmology, and how you measure it. Well, you measure an accelerated expansion of the universe. So you have an accelerated universe. So, and what we would like to know, at least this was the motivation for this work, is there any relation between what we call rho Q, so the experimental energy density in the Casimir lab, and rho lambda, the energy density of cosmology? Is this really quantum driven or has some different origin? A funny effect, just aside, if you put in the numbers, they are of the same order of magnitudes if you calculate joule per cubic meter. So this, are they related? This is the question. And if we can answer this question, we would be really happy. So let's hope to get to a happiness. So let's come back to Casimir, just in a nutshell. It was predicted 1948. It took quite some time until it was first observed, 1997. This is like the simplest formula you find on Wikipedia for the energy density, where A is the plate distance, h bar and so on, you know. So it's an attractive force, if you can translate this energy density to a force. Okay, if you do this project with experimentalists, there are more effects actually. So you have to consider if you think about experiment. So first of all, it's done at finite temperature. So this modifies the dielectric properties. There's even gravitational acceleration between the plates because the plates have mass. And if a precision experiment, you have this Newtonian force between the two massive plates. And you have to integrate over the mass densities of the plate, and then you get a force. So this will be important for us, so please memorize this formula. Another effect which is relevant is a penetration depth, which means that the electromagnetic modes, which have a boundary condition on the plates, are not actually perfect. Yeah? So if this blue thing is the plate, the energy density has somehow penetrating the plate, because in real life, nothing is perfect. So you have this penetration depth. So, and that's about 10 to the minus 8 meter. And this tells us immediately that the energy density of the Casimir experiment is not a global constant, but actually depends on the space-time position where we're sitting at. Okay, so we remember these two things, yeah? Newton's force and space-time dependence. And now to the universe. Well, what better to start off than putting Einstein's equation? We have seen some of them several times. You can go for the cosmological setting, then discover the cosmological constant, which is an observational fact. I just rush over it because you, of course, all know. So there's this expansion parameter for the scale factor of the universe, and this can be interpreted as in terms of a cosmological constant in the Einstein equations, the red thing I showed you before. You can translate this to an energy density just by fixing the units, including C's and G0, Newton's constant, and you get this value here. Okay, and then the big question, which was also asked in the context of this conference, is this of quantum origin? So this was first made by Seldovich in 1967, then made popular by Weinberg, 1988. And I think it's fair to say it's a big theoretical puzzle. And you can reformulate this, also make an argument how it comes about that this is a puzzle. I jump over the argument. So this is the same idea. So you calculate with your theory, quantum theory, the expected cosmological energy density and compare to the measured one. So Q would be calculated with quantum fluctuations and lambda would be measured. And this is, of course, famously a dimensionless number of, well, wrong 120, or depending on which mass scale you choose, 55 orders of magnitude. So that's a lot, and this is my original slide. So an unresolved issue, experimental input needed. So having attended this conference, I learned there are solutions. So it's not unresolved, it's oversolved because I saw several solutions to this thing. So we have several solutions, maybe not as many as 120 orders of magnitude, but we have too many solutions. So we would still need experimental input to understand the problem. Yeah? So the motivation has shifted but not disappeared. Good. So now I want to formulate the two hypotheses of this work. And the first is the question, is the Casimir energy density actually related to what you see in the Einstein energy density equations? Yeah? So is there any relation between the two, or it's something completely different, so we don't have to care? This hypothesis will come with a parameter, will be put on, we call it alpha. The second hypothesis of the work is the cosmological constant, as you see it in the Einstein equations, related to Newton's constant, as you see it in the Einstein equations? Well, this hypothesis we call, we also comes with parameters, C1 and C3 in our model. Well, they seem independent, these two hypotheses. But okay, the second one, for example, we have seen along this conference, when you calculate scattering, it seems like the couplings change, yeah, or RG flow, the couplings change, and they change in a connected way. Yeah? One changes, the other changes. So this is like the second hypothesis. Okay, so let's go in more detail in the first hypothesis. So if you can put on the left-hand side to parameterize the thing, yeah, to measure something, you need an equation. So on the left-hand side, we put the cosmological energy density and ask the question, is this changed if I change my quantum rho Q Casimir energy density? Does this produce a new cosmological real energy density? Does it subtract or add? We don't know, but and the parameter for this change we could call alpha. That's a fair way. So this would be of cosmological origin. That's a quantum modification if it exists. If not, alpha is 0, I'm also happy. And then we would have a modified cosmological energy density. Okay? And now we try to measure this thing, and we can learn something about the problem. But there's a little subtlety here, since I told you before that this is a local quantity. So rho Casimir, the quantum one, it depends on where you are, the cosmological one not. So you cannot really write down this equation and without accepting something. So what we have to rethink, if you want to make this hypothesis, you have to accept for the possibility that the couplings, rho lambda, G maybe also, can be local quantities. Otherwise, we cannot talk about this thing. Yeah? So they need to be variable. So this brings us to the second hypothesis. Are the gravitational couplings connected? So in a sense of running, we are used to that. We have seen that a lot. So if I change lambda, I change G, or vice versa. So they might be connected. That's the second hypothesis. And we put parameters to this connection here. That's all. Yeah. Now, this is just abstract hypothesis. We need a concrete model to calculate something. And this is now what we have been doing, but you might come with a different model. So our model is like a minimal version of this. So what it includes is general covariance. We have just a small deviation from GR. It's a local description, and you only have second order of equations of motion. So which I show you now. This is the model. 5 minutes, okay. So the model is like the Einstein-Hilbert action coupled to matter, but now we allow for this scale-dependent coupling. So all couplings in the theory, the matter coupling and the G coupling and everything, can depend on a scale. So if you write down this action, we don't tell what it is. You can, of course, vary it with a metric, and you get equations, which are the Einstein equations corrected by a term which depends on the scale dependence. Now, to make this a covariant closed system, you can have to do a scale setting. What we propose is a variational scale setting. You have to promote the scale to a field, and then you have it like a scalar field. You have a second equation. So that's all. It's called variational scale setting. It's covariant. And now we need to include also the possibility that everything is small. So we expand for small k, all the couplings which might run, and the couplings in the matter sector. And this automatically includes our hypothesis. Here we have lambda and G connected through K, and here we have matter and lambda connected through K. Now you have to just go and solve the equations for a given problem. And these parameters are the parameters I talked to you about before. So now we want to apply it in 5 minutes to the experiment. So it's a relativistic experiment. You can do the weak curvature expansion of the metric, the weak scale-dependent expansion for G, because you think if it's running, it's weakly running, Planck suppressed, so that's a Planck scale suppression here. Another Planck scale suppression here. And then you have the Casimir matter modes in the Lagrangian, which comes with this parameter. It's basically the Casimir energy. You know, so when you average over the quantum modes of this, you have this rho C here. So, and you get non-relativistic equations, a Poisson equation. What a surprise in the non-relativistic limit. The solution is, as you know, we have seen it before, with a slight change, and the change is that now we have derivatives of the scale here. And we have the scale setting, so it tells us, aha, it's derivative of the energy density, which depends on the Casimir energy density. And this is the modification. So we have the usual Newton equation here, let's say, but we have a slight modification, which comes just from allowing from the scale dependence. Okay, and that's the take-home message almost. So you have a different attraction between the Casimir plates. And it comes from this derivative of the Casimir energy density, which I showed you, changes in the plates. And this can be tested in principle. So we have the two hypotheses. We have a concrete, simple model, and test for these parameters. Here we go. So the experiment of my colleagues is called CANEX. It has been approved this year, so will be built. And it's so precise that it can measure both the Casimir force and the Newton force. And then you can ask, okay, do we see the Newton force as usual, or do we see a deviation from that? And from that, you can draw conclusions on these parameters. So what we now impose, since it's not measured yet, is just we want that this is a small, so the curly f and the usual f is a small correction. Yeah? Must be smaller than 1. And importantly, you have this spatial dependence of the Casimir energy density. And since this appears in the equations, this can make a huge effect. And what we found to our surprise is that these parameters, which we expected to reduce them of order 1, because typically when I do quantum gravity experiments, the proportionality factor, I cannot make strong suppressions because it's all Planck suppressed. But here the thing cancels out, and we get a very strong bound on these parameters, which is surprising and quite cool. And now my time is to 1 minute, so take-home message. So the take-home message is not really our model. The take-home message is take these two hypotheses, which I think are reasonable, good questions to ask, and if you do this, you find possibly big corrections to the Newton potential in this experimental setting, unless these hypotheses are small parameters. These ratios are small. So, and this will be tested. This is, I think, very cool. Second take-home message, since this happened in our model, and I guess it's such a generic thing, it should happen in different models. So if you have a different model which has these two hypotheses implemented, please look into that and make your predictions. Thank you very much. And there's more things we want to do, of course.
Okay. Shut up.
Questions?
Okay. So, are there questions? Yes,
Yep.
we have one
What we hear
one
you.
short question.
For the recording. Yeah.
Thank you very much for the talk. So we had a really interesting talk a few days ago about how to measure this kind of effects, gravitational effects in a lab. And they were explaining us that it was really, really difficult to isolate many of the environmental noise. Where is this experiment going to be located? Is it in Santiago or?
No, this is in Vienna.
In Vienna.
With a lot of noise, as we learned in this other talk. Yes.
No, because I was thinking that in Santiago you have earthquakes all the
Yeah.
time.
You can kind of rid of it because the plates are oscillating themselves. So you always measure these differences.
Okay.
But okay, I'm not an expert in that, so
Sure,
I cannot really. I just trust.
Great. Thank you.
Okay, let us thank the speaker again.